Hi, in this video we are going to look at a very interesting topic called approximation algorithms. We will also look at a particular problem called vertex cover problem, which can be solved using an approximation algorithm. The outline of this lecture is going to be like this. First we will see what is an optimization problem and how to deal with such problems. Then we will look at the role of approximation algorithms in solving such problems. We will also discuss in detail how to solve the vertex cover problem using an approximation algorithm. And finally, we will be doing a proof for the performance guarantee of this algorithm. Approximation algorithms are used in solving many of the optimization problems. So it is important to understand what is an optimization problem. The goal of an optimization problem is to find the best solution from all the feasible solutions. A large number of optimization problems have exponential time complexity and are said to be NP hard. Some of the examples from the computer science domain are the traveling salesman's problem, or the TSP, 01 knapsack problem, and vertex cover problem. It is practically impossible to design algorithms that can find the exact optimal solutions for all instances of the problem in polynomial time. So it is important to understand how we deal with such NP-hard problems. It is also to be noted that the optimization problem can be either a minimization problem or a maximization problem. For example, TSP is a minimization problem, whereas 01 knapsack problem is a maximization problem. In TSP, we want to minimize the cost of the route, and in the 01 knapsack problem, we want to maximize the profit. Usually there are three ways of dealing with NP-hard problems. One is to use brute force algorithms. The second one is to use a heuristics-based algorithms. And the third choice is to use approximation algorithms. We will see each of them one by one. In a brute force algorithm, we will enumerate all the feasible solutions and then find the optimal solution from the list of feasible solutions. So the problem here is that you have no guarantees on running time. We have already seen in one of our previous lectures that in a TSP problem, the brute force algorithm takes 77 years to solve a 21 city problem. Another way is to apply some heuristics. Heuristics is about applying intuitive algorithms which are guaranteed to run in polynomial time. The problem here is that you don't have any guarantees on the quality of the solution. It means that for some instances of the problem, the heuristics algorithm may work well, but for some other instances of the problem, it may not work well. Here comes the role of approximation algorithms. Approximation algorithms are guaranteed to run in polynomial time and are also guaranteed to get a solution which is close to the optimal solution. And the closeness is already defined. So there is a challenge. We need to prove that the solution's value is close to the optimal value without even knowing the optimal value. Now let us look at the definition of an approximation algorithm. So if you are given with an optimization problem P, an algorithm A is said to be an approximation algorithm for P if for any given instance of phi, it returns an approximate solution that is a feasible solution. Now there are two types of approximation algorithm. One of them is called absolute approximation algorithm and the other one is called relative approximation algorithms. Let's try to understand each of them. So let P be an optimization problem, A an approximation algorithm, and I be an instance of P. Also, A star of I is the optimal solution for the instance I, and A of I is the solution generated by our approximation algorithm. Now, the algorithm A is said to be an absolute approximation algorithm if there exists a constant k such that for every instance I of P, A star of the modulus of A star of I minus A of I is bounded by is less than or equal to k. The example for this is planar graph coloring. Similarly, A is said to be a relative approximation algorithm if there exists a constant k such that for every instance I of P, max of a star of I divided by a of I, comma, a of I divided by a star of I is less than or equal to k. So the vertex cover approximation algorithm is an example of a relative approximation algorithm. It is evident that we are applying the modulus function here to accommodate both minimization and maximization problems. Similarly, we are taking the max of both to accommodate both minimization and maximization problems. Now we will focus our attention towards vertex cover problem. We will understand what is a vertex cover and how to apply an approximation algorithm to come up with a feasible solution which is close to the optimal solution. So given a graph defined by G is equal to V comma E, where V is the set of vertices and E is the set of edges, a subset C of all the vertices is said to be a vertex cover if at least one vertex of every edge of G belongs to C. It simply means that the vertices in C will cover all the edges in the graph. And our goal is to minimize the value of C. It will become more clear once we look at an example. In this graph, suppose I am choosing vertex 1, 4 and 7 and checking that whether it forms a vertex cover. To do so, we should look at all the edges covered by vertices 1, 4 and 7. By saying the edges covered by vertex 1, it means that the edges having vertex 1 as one of its endpoints. So the edges covered by vertex 1 are 1, 2, that is this one, 1, 5, 1, 5 and 1, 4. Similarly, the edges covered by vertex 4 are 4, 3, 4, 1 is already covered, then 4, 7, 4, 5. And the edges covered by the vertex 7 are 7, 5, 7, 6, 7, 4 is already covered. Okay, these are the edges which are covered by vertices 1, 4 and 7. We can see that all the edges are not covered. That is 2, 5 is not covered. Similarly, 3, 6 is also not covered. So as per the definition of a vertex cover, the set 1, 4, 7 is not a vertex cover. It is not a vertex cover. Now let us check whether the set 1, 2, 3, 5, 7 forms a vertex cover. Now I will mark all the edges covered by vertex 1, 2, 3, 5 and 7. So the edges covered by 1 are this one, and this one. The edges covered by 2 are this one, and this is already marked. And the edges covered by 5 which are unmarked are 5, 7, 5, 4. And the edges covered by 7 are 7, 6, 7, 4. And the edges covered by 3 are 3, 6 and 3, 4. Now note that in this case we are successful in covering all the edges. So the set 1, 2, 3, 5, 7 is a valid vertex cover. So the set C given by 1, 2, 3, 5, 7 is a valid vertex cover. And the size of this vertex cover, that is modulus of C, is equal to 5. Now the question is whether we can do better. That is, can we minimize it further? The minimum value of C corresponds to the minimum vertex cover. Remember that there can be more than one minimum vertex cover for a graph. Now let us check whether the vertices 1, 4, 5, 6 forms a vertex cover or not. Now let me highlight the edges covered by 1, 4, 5 and 6. The edges covered by 1 are 1, 2, 1, 5, 1, 4. The edges covered by the vertex 4 are 4, 5, 4, 1 is already covered, 4, 7 and 4, 3. Similarly, the edges covered by 5 are 5, 7, 5, 2. 5, 1 and 5, 4 are already covered. Now the edges covered by 6 are 6, 3 and 6, 7. 6, 3 and 6, 7. So we can see that all the edges are covered. So it clearly indicates that the set 1, 4, 5, 6 is a valid vertex cover and the size of the vertex cover is 4. Now you can pause the video for some time and try to find out other vertex covers with a size equal to 4. You can also check whether it is possible to have a vertex cover having size less than 4. In fact, in this example, we cannot have a vertex cover whose size is less than 4. It means that the minimum vertex cover of this graph has a size of 4. The figure B, C and D shows some other possible vertex covers of this graph. Note that the vertices inside the vertex covers are marked in red. Figure B is a trivial vertex cover in the sense it contains all the vertices of the graph, and figure C and D contains vertex covers having a size of 4. Now let us estimate the complexity of a brute force approach which can be used to solve the vertex cover problem. Suppose that we are given with a graph having n vertices. Now if we are making use of a brute force approach, we have to generate all the different subsets of this set and check whether they are forming vertex covers. And among all the subsets which are forming vertex covers, we want to choose those vertex covers which are the minimum. Now we know that for a set having n vertices, there are 2 raised to n different possible subsets. And once we generate all these 2 raised to n different possible subsets, then we have to find the minimum vertex covers from that. So roughly the complexity of this will be big O of 2 raised to n. And big O of 2 raised to n is an exponential complexity. So the running time of this algorithm will increase exponentially as the value of n increases linearly. So for large values of n, it will take months or years of time to compute the vertex cover, minimum vertex cover. So the only way is to depend on approximation algorithms which can give us close enough solutions without much delay. So we will look at one such approximation algorithm in the next slide. We will analyze this algorithm step by step. The first step is that we are initializing the solution set as a null set, and then we are arbitrarily picking an edge uv from the set of edges. Now we will add the vertices of this edge to our solution set. That is why we have written C equal to C union u comma v. And once we have added the vertices of that edge, now we will remove all the edges incident either on u or on v from the set of edges. And we will repeat this process until all the edges are removed from the edge set. And once all the edges are removed, then the vertices present in your solution set C will be surely a vertex cover. Finally, we will return the solution set C. This is the formal version of the same algorithm represented in the form of a pseudocode. You can see that this is very similar to the informal algorithm which we have seen. Here also we start by initializing our solution set as a null set. Then we will check whether the edge set is null, and if the edge set is not null, we will add an arbitrary edge uv to our solution set, and then remove every edge incident on either u or v. And these steps will be continued until the edge set becomes null, and finally we will return the value of C. It can be verified that the time complexity of this algorithm is of the order of big O of v plus E, where v is the set of vertices and E is the set of edges. And we know that the set of edges cannot be more than v square. That is, if the number of vertices are represented by n, then the number of edges, the order of the number of edges cannot go more than n square. So it means that the complexity will be of the order of n square. And we know that order of n square is a polynomial complexity. This concludes the fact that this particular approximation algorithm has a polynomial complexity. Let us now see how the vertex cover algorithm works on this graph. As per the algorithm, we have to initialize a solution set C as a null set and an edge set as the set of all the edges which are present in the graph. So you can see there is a solution set here which is initialized as a null set and an edge set here which contains all the edges in the graph. The next step is to check whether the edge set is null or not. If it is not null, then we will choose an arbitrary edge uv from the set of edges and add it to our solution set. And after adding it to our solution set, then we will remove every edge incident on either u or v from our edge set. And this will be continued until the set of edges becomes null. And finally, we will return C. In our case, initially the edge set contains all the edges which are present in the graph. So it is not null. So let us choose an arbitrary edge, say 1, 2. 1, 2 from the graph and add it to our solution set. So 1, 2 will be added to our solution set. And then we will remove every edge incident on 1 or 2. So we'll be removing 1, 2, 1, 4, 1, 5 and 2, 5. So we'll be removing 1, 2, 1, 5, 1, 4 and 2, 5. And now again we will check whether the edge set is not null. So again we can see that the edge set is not null. And then we will choose another arbitrary edge uv from the set of edges. Let us say I choose 5, 7 as the next edge. 5, 7 will be chosen as the next edge. And now we will add it to our solution set. So 1, 2, 5, 7. And then we will remove every edge incident on either 5 or 7. That means 5, 4 will be deleted. 5, 7 itself will be deleted. 7, 4 and 7, 6 also will be deleted. Now let us delete those edges from our edge set. So 4, 5 will be deleted. 4, 7, 5, 7 and 6, 7 will be deleted. Now again our algorithm checks whether the edge set has become null. We can see that there are two edges remaining, 3, 4 and 3, 6. So our algorithm will continue and choose one of the edges as an arbitrary edge. Let's say the algorithm chooses 3, 6 as the arbitrary edge here. So 3, 6 will be chosen as the next arbitrary edge. Now let us add 3, 6 to our solution set. 3, 6. Now we will also delete the edges incident on either 3 or 6. So 3, 4 will be deleted, 3, 6 itself will be deleted. Let us now delete those edges from our edge set. So 3, 4 and 3, 6 will be deleted. Now we can see that our edge set has become null and our loop will now terminate and it will return the value of C. So C contains a valid vertex cover which is 1, 2, 5, 7 and 3, 6. So the approximate solution returned by our algorithm contains 6 vertices which can be represented by writing modulus of C equal to 6. Another important observation here is that the edges chosen by our algorithm are independent edges. That is, they don't share a common vertex. This is something which will be very useful when we prove the performance guarantee of this algorithm. While proving the performance of this algorithm, we have used a term called maximal matching. So it is important to understand what a maximal matching is. So before understanding what is a maximal matching, we should know what is a matching. A matching is nothing but a set of independent edges or a set of edges without common vertices. So a matching becomes a maximal matching when you cannot add any more edges to it. Now it is evident that the vertex cover that is chosen by our algorithm will always be a maximal matching. For example, the edges present in our solution set were 1, 2, 3, 6 and 5, 7. 1, 2, 3, 6 and 5, 7. And these edges always forms a maximal matching. So the maximal matching in this case is given by the set containing the edges 1, 2, 3, 6 and 5, 7 and is represented as shown. Now it is clear that the number of elements in C given by modulus C in this case is 6 and the number of elements in the maximal matching set given by modulus of M is 3. So it is evident that the number of elements in the vertex cover set given by modulus of C is always equal to 2 times the elements present in the maximal matching set M. We have already seen that every approximation algorithm should have a performance guarantee with respect to the optimal solution. The performance guarantee of this approximation algorithm is defined like this. If C is the vertex cover found by the approximation algorithm and C star is the minimum vertex cover or the optimum vertex cover, then we can always prove that modulus of C is always going to be less than or equal to 2 times C star. Now let us try to understand its proof. We have already made it very clear that the vertex cover chosen by our approximation algorithm will always be a maximal matching. It is also known that the algorithm runs in polynomial time. Now, C star should cover every edge chosen by our algorithm in our vertex set, which is a maximal matching, say M. And we already know that all the edges in M are independent edges, that is, they don't share a common endpoint. Now we can clearly argue that C star should contain at least one of the endpoints of every edge in M, which implies that modulus of C star should always be greater than or equal to modulus of M. This allows us to write 2 times modulus of C star is greater than or equal to 2 times modulus of M. Now we already know that 2 times M is nothing but modulus of C. So we can clearly write that modulus of C is less than or equal to 2 times C star, and hence our performance proof is complete. This can also be verified from the example which we worked out. There we knew that the C star or the optimum vertex cover had a size of 4, and we claim that our approximation algorithm will definitely have a size less than 8, and we have already seen that the approximation algorithm returned a size of 6. So 6 is always less than or equal to 2 times 4, which holds good, and thus we can verify that this proof is correct. Now, as an assignment, you can apply approximation algorithm on the above graph and find the vertex cover set and the number of vertices in that set. You can also find the minimum vertex covers using brute force approach and then verify that modulus of C is always less than or equal to 2 times modulus of C star. In the next video, we will be dealing with another approximation algorithm which will help us to solve the problem of planar graph coloring. See you then. Thank you.